Hello, everyone. I'm very honored to give a talk on behalf of my team. We have published a paper on IEEE transaction on industrial informatics, TII in short. So the talk for today is called Federated Learning-Based Synchrotron X-ray Microdiffraction Image Screening for Industrial Materials. And I'm going to explain the talk as follows, starting with the background, with the synchrotron X-ray facility, with the motivation, especially with the efficiency and privacy concern, and the methodology, the machine learning-based image screening, and also with the federated learning-based image screening, and the applications and result followed by conclusion and discussion. So first of all, X-ray has been discovered since in 1895 by a scientist. We can call him Professor Röntgen, discovered that, and then follow with this. Max von Rode discovered the X-ray diffraction through crystal in 1912. So they both were awarded with the Nobel Prize. So since then, X-ray has been used to discover what's inside the human bodies and also other animals and all different type of organisms. So we can use the Bragg, since he has proposed a Bragg's law, that can help to utilize X-ray to diagnose the internal structure of the crystal, and it can be used in scientific research. So X-ray in synchrotron facility, industrial and scientific world, has been used in high energy physics and also quantum physics in particular, and to understand how particles move. So a synchrotron is a particular type of the cyclic particle accelerator in which the accelerating particle beam travels around a fixed closed loop path. So they can simulate a lot of scientific research. So that looks like something like this. So you can then have lots of things, and then you can then make the particle travel in a very fast speed. And this kind of facility consists of the linear accelerator, booster, storage ring, and beam lines. So that you can then perform many experiments according to your requirement. And the experiment stations, and they are all the stations in the world has been used at least since 2005. This is the information if you're interested to find out. And that has been extremely useful to benefit from those research. So just to recap, if you do not know much about physics, so this is how it looks like when you have the beams, and then after you get a diffraction. And this is called Bragg's law behind the new XRD services. And then the scientists can then perform those and then get the beams and then on the particle, and just to observe what will be the situation and to collect the outcomes. And you can then perform an experiment accordingly, and you can get the results in such a way. So illustrations of the new XRD for industrial material analysis, so you can investigate water, nylon, motor oil, harder rubber, and to understand inside those materials how the particles will behave. And then the motivation is that the X-ray synchrotron facilities are useful, while two challenges appear, because although it's highly efficient and having our goals achieved, there are two issues: efficiency and privacy. Efficiency problem means that the new XRD cannot work with a massive image flow, given with plenty of images during a short period of time. Because imagine that within a short period of time, there's a massive amount of images. It cannot be able to cope with this. And of course, it's hard and expensive for human being to annotate, because you have to verify one by one. Is laborious and time-consuming process. And the privacy problem is that the results from many facilities or samples are from different sources, even in the same area, because you do not know what they are, and because you need to keep all of the images private, and isolated diagnosis is not efficient, or sometimes bring some misclassification, because we have to ensure privacy is all kept throughout the process, and to maintain both. And we are aiming to fix both problems and improve those efficiency and privacy problem as scientists. So I'm going to explain the methodology as follows. There are two things you need to know. First of all, the basic machine learning still face difficulties. Why? Because there are many deep learning tools that can help classify the images. However, the supervised learning can utilize the expert annotation, and the domain knowledge will also be required, because if you do not have the domain knowledge, then you may not utilize the learning process effectively. And the various machine learning or neural networks, or both, we call that learning neural networks, can be adopted to screen different categories of the new XRD images. So basic machine learning, therefore, with the neural networks, is adopted to address efficiency problems. So now we try to focus on efficiency, but then we need to know some information from different machine learning instances. And new XRD service users are not willing to share the original images for machine learning due to privacy concerns, because those images are, the result of their years of investigation, and they can be very valuable for scientific research, especially if you need to be the first person to publish certain new discoveries, or you want to use those results for the funding. Therefore, you do not wish to share your images. So the issue is that if we do not know the client's images, and how can we still achieve our goals? And that is a very challenging scientific problem we have. So just to go through with some theories without going too much on that. So first of all the models we have should have a parameters in the way we call W. So you initialize by the server with a WO for time O, and then synchronously, then you keep on 1, 2, and then towards the end. The client apply the model of the local data. For each round, the clients will upload to the server, and the model parameters, the gradient, the losses, and the local training processes. So with the omega, they show the different parameters, the gradients, and G with the gradient, L for losses. And once the server has the updated images from the client, and you will be designed for the algorithm to update the new model and broadcast to the client is what the federated learning is doing for the next round of training. And the point is that we have the aggregated these messages. We need to understand what the messages are and then aggregate them. So while you are processing images from scientific research, the images with hit or maybe labels require investigation and miss would be discarded. So what does this mean? It means that we do not know what the images on client side due to privacy concerns. So our algorithm should be able to identify or logically guess correctly. So there are three scenarios. One is hit, means that you get them right. Maybe it's that sometimes you get it right, sometimes not. Then miss means that you probably miss it and you may have to do it again. So a priority will be focused on the correct prediction of hit or maybe. The reason is that there's still a very high percentage of miss under such circumstances, since we do not even know what the scientists' images are, and every time the experiment may be very different from the previous one, and it can be done by different scientists. Therefore, there is a very high percentage. But having said that, we should always asking for or seeking any improvement or any methods for improving the accuracy to get a hit or maybe. When you get a maybe, then you can have other methods to identify a very accurate result later on. So in order to do this, we have a thing called prediction factor, PF. So this NI label is the number of sample label as miss or maybe, and NJ true is the number of sample that should be categorized as miss or maybe. So this is presented by this formula with a miss or maybe, but of course we will try our best to get a hit. So the algorithm would sample the loss from the client, from the distribution PF. The client loss with the highest PF would then impact more to the update to the client weight. So then you can have this client weight and then with the prediction distribution, because when you accumulate all enough weights, then you have to also apply that to our PF prediction factor, so that the factor may get better and better every time. The PF distribution is the sum of all the PF, and then on the inverse to the sum of all the PF, then you multiply them together. And then from the point of view that the local data optimization, the data class that appears more frequent will be the major class KMax. So KMax is also, we have to get all of them together, and then with the gradients, because when you're doing this scientific research, we do a lot of research. Therefore, the gradient will then determine what sort of regression we may perform, and then also we can have more information in our paper if you can read them. But now I would like to focus on our algorithm. What is it used? How it can be used? So this is federated learning. As you can see, federated learning will allow parameters to get into that, and then update the parameters back, and then so that you do not store any sensitive data. And then once it's used, then you can then even move it or take it. So in our case, what we do is that input with data samples, initial global model weights, and the initialization is the model weights on the server, W, O, and the initial client weights. And then for T1 to T, for the loss of accuracy, achieve a stable level. We first of all broadcast server weights to clients. So then we broke all the clients are getting the message to process the images, and the local models are trained with the client data, and the client then uploads weights, gradient, losses, prediction factor to the server. These are the major parameters, and the server updates with the client weights, and the global weights, and the broadcast updated this. So once it's done, it then broadcasts so that no one can aggregate data from many clients. Server knows only parameters of the model. No one knows any data except the client itself. And bidirectional communication to ensure that this can be done. So we then achieve privacy by this way. So only you know what you are having the processing with, and nobody else would. And once we have finished the processing, and then it's all done. So this is the formula to present the number 4, to have the weights. So we get it updated. Once you update it, then you broadcast to it, and therefore then we then get the results at the end. So handling new problem in federated learning, unbalanced data in actual applications by proposing novel client sampling algorithm, because we know that there are always problems with unbalanced data, and sometimes even we try our best to perform experiments. Not every time we can get the same results, and of course it also vary with different sizes, different values. So we propose a novel client sampling algorithm to handle unbalanced data distribution and hybrid training schemes. So we can then improve the communication between federated clients and servers. The data volumes in different classes are unbalanced in most of the applications. The mixed images are dominating among the new XRD images. So our experiment shows that although we can maintain privacy, we can get a job done in a good amount of time. However, the thing is that due to the complexity of the images, we get, in this example, then we get more than 100, we get a hit. But also the miss is dominant. It's not just a problem for that, but it's a problem due to the fact that scientists have their own images, and we do not even know what they have, because we are supposed not to even know. The server should just serve for the purposes. We are not supposed to know. However, it's also important that we have to process them correctly. Otherwise, you may also not getting the right type of results. And then you can see maybe it's the one that you can then further analyze so that at the end you can then get the right data. However, there are still ways to improve, and we have to also go for better ways to understand. Perhaps the images itself should have certain information for other scientists to know. You don't have to know everything, but perhaps the scientists should know a little bit of something when you are using the facility to run. And as you can see, if you get it correctly, then you will get the data. Of course, the server itself will be able to see. So now the second algorithm, it works with different clients. This is how it looks like. The initial model aggregated, updated models. So you have all the clients in places, and the client trains on the local data to get your own models. Then after that, you have the clients maybe offline, part of them to participate. Of course, we have different weights, such as the weight 1 to assign to client 1, the weight 2 to assign to client 2, and weight WN to assign to client. So in this order, so in this way, then we can have the asynchronous learning. Why? Because the synchronous will be the best. However, when the server is very busy and we have so many clients, you may not be able to get the result in real time or immediately. So you will take a little bit of time. So this is called asynchronous learning. However, we should not take such a long time. In theory, if we have the federated learning in the satellite communication, such as Starlink, then of course the jack time or the lag time will be very short. So asynchronous learning, in this case, we have the local weights, the prediction vector, losses, and gradient from client. And the processing is that while the learning zone check the client which is being pulled. If the number of uploads relevant is less than the number of clients, then we do asynchronous model updates. Otherwise, then we do synchronous update. Why? Because it's that if we do not have enough, then we will better let them stand by until the task or jobs beforehand or finished. But then if we have enough power, enough resources, then we can get them as a synchronous learning. So first of all, we have to identify whether can we finish the request from our resources. If yes, then we go for synchronous. If not, then asynchronous. So asynchronous update, then you have different scenarios. You would push the client's upload to the server, which check the times of the client being pulled. If the client is never being pulled, then add it to the update set. Otherwise, adjust the client weights epsilon times to original value. Then add the updated local parameters to the previous round ones to generate a model. And in this model, we'll get everything updated, called W updated. And the synchronous updates will then push all the client uploads to the server to the regular model updates. So in this case, we have to perform an experiment. From an experiment, we use a very well-known models. Of course, we then run with ResNet 50, DenseNet 1-to-1, ResNet 18, VG19. So what does that mean? It means that we have the training time and inference time. Inference time is to identify whether we then can then get the images correctly. Of course, currently, human expert will be still the important process, probably. But then we were, in the process of making it automation and with a high accuracy. So now, if we do it individual tasks as an industrial application, it should take between 2.75 to 3.05 per job or per task. However, because training will always take a long time for that, so we then this is the unit of time. If we then perform it 29 times, and it will between 312 to 322 seconds. And as you see that there's also a general trend for this. And then in this data set, we find that the inference time is much shorter because it's probably it's much easier for the algorithm to identify them correctly or get the answers correctly. But then in this data set, you find that sometimes you go over to the training time, sometimes below it. And then in this one, we have a much lower inference time. So compared with the baseline, the model has achieved 21% accuracy improvement. That's a vast improvement. And with the VGG19 for 14%, and ResNet 50, 70%, and ResNet 18, 25%, with a DenseNet 1-to-1. The accuracy improvement is then realized with a federated learning level across different neural networks, not due to the change of underlying neural network, the model can save more effort on the expert annotation and lower the image misclassification rates with improved accuracy. Of course, this is an ongoing process. And then further federated learning with the physics law information. So we put more weights to a prediction factor. Why? So if we put more weights, we then can get the result better. So hue is important. Why? Because it can make a distinguish differences when the images have a higher requirement on the resolution or fine details. And the sparse spots bring more attention to some areas. And this is an example because you can see that after running our federated learning, you can see that the colors is clearer, especially when you're investigating certain biological signs. Then certain, for instance, humors, and you cannot see things clearly, that's not good. Maybe that can be the cancerous cell hiding somewhere. So this is just example to show after running our algorithm, if you scatter, maybe you can still get the result, but maybe not in a good quality, you still miss. And miss means that you didn't get them correctly. So miss, sometimes we can get the images correctly, but when you are doing the further processing, it's not getting to the good standard, and that is called miss also. So miss is not just not to get the right images, but also the quality is not good enough. When you are doing scientific research, there is a very high demand of accuracy and not perfection, but quite close to 99% and above. So our algorithm can bring many benefits regarding to accuracy and convergence. There are still some limits existing for this algorithm. For instance, when data distribution on the clients are relatively balanced, and the sampling of the unbalanced data might introduce extra computation complexities, which may affect convergence negatively. However, in good circumstances, we can still differentiate the details, and we can then see those images very clearly. And then the experiments also follow. Then we run those for data sets, and then we have the PF, which is always better than the baseline. So by using federated learning, our predictive distribution goes above. So it then increases our prediction rates and also improve the overall quality in general. And we save the work for experts, save expenses for training specialists with domain knowledge, incorporate the domain knowledge into normal machine learning or deep learning processes, because we then can together with deep learning, and then we can then even get a better result than the help to improve the efficiency on achieving intelligently classification. And then the applications as follow. We can then utilize sample information from different clients and facilities. We can preserve the privacy of the local clients, and we can make client happy with the improvement on their local tools without any personal information leak. And furthermore, the boost the process from supervised learning to unsupervised learning, and we can have that very smoothly done. So image sample subgroups are as follow. We can try those things. So these are the things that you may see in other scientific research. So there are different instances we can see. So then we perform those scientific experiments with both synchronous and asynchronous training. So then we can see that under the asynchronous circumstances, accuracy versus time, as you see, when time goes by, at the very beginning, it then picks up the accuracy between 70 plus to 80 plus, and then around 85% plus, like above. And then with synchronous learning, of course, you may not get a high accuracy, but then synchronous learning, because sometimes you may miss certain information, although it's real time and more efficient. However, sometimes you may have a double check. That's why asynchronous learning, although it may be fluctuating, but then you are within a better percentage of accuracy. Yeah, and then when the time goes by, then of course, synchronous learning have a slightly better accuracy. And then we then can compare the synchronous training again, and we can see that asynchronous then reach a very high percentage of accuracy at the very beginning, and then keeps around 85%, very, very closely. And then with the synchronous learning, then when time goes by, it then surpass 85%. So if we have sufficient time, synchronous learning will be more accurate because you may have a better prediction rates and also get that. So the communication cost for offline clients in the asynchronous scenario, the vertical axis, the accuracy, and the percentage, and the horizontal axis, number of communication rounds. The time cost for the offline clients in the synchronous scenario, and similarly with the same meaning. Percentage of accuracy and time unit. So by using our more methods, the edge devices on the client side can be equipped with a federated software package, or even be deployed with a customized computing software. Once the software package or hardware is ready, then we can, instead of asking the expert to do the annotations, the clients can have the images or samples labeled intelligently and automatically by the federated learning paradigm when the data flows into the pipeline without human intervention. And both synchronous and asynchronous training methods are integrated in our hybrid training scheme to improve communication between clients and servers. So we need to have both ways, because we may, not to miss anything, and we may also facilitate the advantages for one or the other. If you want to reach accuracy earlier, then asynchronous training is the one. But then you want to have a long-term accuracy, then of course when time goes by, a synchronous one is better. So we propose a federated learning based on the new mXRD image screening method with physical law informed rules. We improve the screening without disclosing the original data across servers, and we address difficulties in accurate new XRD images screening due to the lack of label or industrial samples and privacy concerns of industrial users of the new XRD services. This is our main research contribution, because we're not supposed to know them. However, our method will be able to get them correctly to a good extent. And even we get the images, but then we have to then fix the image quality issue, because those scientific research have very high demands on it. And of course, we are still in a process of improving. The local data will never be our corresponding clients during the training process. This is a good sign, because federated learning can keep the privacy on the top and get the job done, and then have the high accuracy. And on the way for further improvement, the privacy and confidential data of the local clients are protected in this sense. Then we can improve on the hit and reduce on the miss. Of course, this is a long-term strategy that we always want to have a better and better outcomes for that, achieve a greater accuracy and efficiency while maintaining privacy. And the current will normally will not take those things into account. That the realistic industrial consideration or constraints, the normal machine learning or deep learning is not account for the privacy of the original samples. The expenses of the industrial sample labeling would be reduced, and a heterogeneous sample distribution are tackled. So we have explained our paper, and for the details, please, we would appreciate you to read our paper. We will be grateful if you can consider citing our paper if our work is relevant, helpful, or inspiring to you. Thank you so much for your time to listen. I'm very honored to give a talk, and we wish you all the best. Maybe we will see you again.